Welcome back to the sequence of videos about limits. In this video, I will be talking about two examples. How to find limits if you don't have a graph of the function, and vice versa if you do have a graph of the function, but you don't have an expression of the function instead. So I wonder which one is easier for you. It really depends on the person. In this case, they ask us to sketch the graph of the function from the given expression. F of x is minus x if x is less than -8. It's 64 minus x squared if x is between -8 and 8. And it's also x plus 1 if x is greater or equal than 8. And that's what we call piecewise functions, when they are glued with pieces. Sometimes those pieces match pretty well and the function is continuous, but sometimes it's not. If you think that those functions are annoying and you don't understand why we teach you these functions, actually most of the functions in the real applications are piecewise. Even your utility bills, these ones you're paying $50 for the, say, AC in summer, then the temperature increases, so you use AC more, then it becomes cooler, you turn it off, and so on and so on. Piecewise functions. So this is the way I like teaching these problems. I like to name each situation, or basically each expression, as 1, 2, and 3. And I also like to represent what is happening with the function. So this is my x. When x is on the left from -8, then function number 1 happens, and the function number 1 is minus x. When x is between -8 and 8, then function number 2 happens, and the function number 2 is the quadratic function, 64 minus x squared. And finally, when x is greater than -8, then the function number 3 happens, number 3. That's the x plus 1 function. So now you have some kind of, you can imagine what is going on, and then there's 3 different pieces on the left from -8, between -8 and 8, and on the right of 8. So now they want us to find, if we can, the limit of this function as x approaches 8, here this 8, or basically this point 8, and also the limit as x approaches -8, because those 2 points are troublemakers. So they want us to find out what is happening at those points. But to find that out, you first need to calculate left and right limits, which are also called side limits. Side limits. Let's find what happens with x, with a function as x approaches 8 from the left and 8 from the right. Do you see that little tiny negative sign? It doesn't mean that it's -8. It means we're approaching 8 from the left, like this. That's how I usually imagine it this way. So what kind of function should I use when x, oh no, that's not 8, that's -8. That's a weird order. I would actually start with this one because it's easier to represent this way. So let me do that instead. I'll use different colors, say pink. What is happening as x approaches -8 from the left? This minus sign is only needed for you to choose the function where you're going to be plugging -8. I'm approaching -8 from the left. What kind of function will I be using here? You see, from this nice notation, I already know the answer. Function number 1. And the function number 1, I will even put a note here, and the function number 1 is minus x. So I'm actually working with the limit as x approaches -8 from the left, when we are plugging everything into minus x. Well, let's plug -8 into -x, and the answer is +8. -8 gives me +8. So as you can see, that negative sign, we don't use it anymore when we plug. We only use it to choose the function to work with. What is happening with the same point as x approaches -8, but now from the right? When x approaches 8 from the right, here it is, then I'm choosing the function number 2. Make sense? So I will do it a little bit here, like this, number 2. And I will make a note, number 2. What is the function number 2? That means I'm talking about the limit as x approaches -8 plus But in this case, I'm plugging everything into 64 minus x squared, because it's exactly what happens when x approach minus 8 from the right. Minus 8, see, from the right, like this, standing literally on the right from minus 8. Let's plug negative 8. Negative 8 squared is 64. 64 minus 64 is 0. What is the conclusion? Well, you know the left limit should match the right limit in order for the limit at the point to exist. 8, let me write down, 8 did not match with 0, so the limit as x approaches minus 8 of this function does not exist. Okay. Let's repeat the same situation with the point 8. What happens as x approaches 8 from the left? Then x approaches 8 from the left here. What kind of function would I choose? Still function number 2. Here it is. Because I'm approaching 8 from the left like this. And the function number 2 is 64 minus x squared. And I don't have to write it again. 8 minus 8 gives me 0. Not 8 minus 8. 64 minus 64. Finally, when I'm approaching 8 from the right, like this, then I'm choosing function number 3. That's the one we did not do before. Function number 3 is limit as x approaches 8 from the right of x plus 1. Plugging 8 into x plus 1 gives me 9. And as you can see, again, 0 did not match with 9. Left limit did not match with the right limit. So the limit D and E. And I can even write down, if you want for you, D and E, because for both cases, left limit does not equal to the right limit. Right limit. Very interesting. Let's sketch the graph now. To sketch the graph, I'm going to use x and y axis. X and y. And actually, we don't know that it is y. We call it f of x here. It may be g or something like that. Then we know that there's something happens at negative 8 and at 8. There's some kind of symmetry definitely here. Between negative 8 and 8, this is the parabola concave down. Parabola concave down, you even can find the vertex, and it looks like this. Parabola concave down. Now, on the left of negative 8, there's a function y equals minus x. If I plug minus 8 into minus x, it gives me plus 8. That's exactly where this connection did not happen. So this is the graph of the function. Let me use the same red color to show you that this is the same graph of the function, like this. And on the right, it's a line as well, x plus 1. And x plus 1, if you plug 8, the answer is 9, so that's the height. It looks like this. Now we just need to be careful where the point is closed and where it is open. As you can see, it cannot be closed everywhere. So let's figure this out. Which one is which? That comes from the calculation. Left limit as we are approaching minus 8 from the left is 8. That means this point is closed, not 0. So this point is open. And this is height 8. Then right limit as x approaches 8, this one, from the right is 9, not 0. So this point is closed and this point is open. And this is 9. And you literally can even write it down like this. When I'm approaching negative 8 from the left, the height is 8. When I'm approaching negative 8 from the right, the height is 0. We got that. Here it is, 0, this one. When x approaches 8 from the left, the height is 0. When x approaches 8 from the right, the height is 9. And this is the graph of the function. Let me write down y equals x plus 1 and y equals 64 minus x squared. Actually, we're not supposed to write y because we don't know the name of the function. So let's just put f of x everywhere. Because it might be not y, it might be like g or m or anything your imagination can give. Y is just a standard notation for many examples. So what can you claim? We can claim that we're experiencing a jump, or the function has a jump at both points x equals -8 and 8. It literally jumps from the height 8 to 0 at -8, and then jumps from the height 0 to 9 at 8. And that's interesting. That's type of discontinuity. Now, let's do one more example, but a little bit faster, and you will be super professional in these types of the examples. In this case, the graph is given, and they just ask us to fill in the information. And I'll go faster, and you can try to do it yourself right now. Just pause and see. What is happening with the function as x approaches -1 from the left? Where is -1? Here is -1. When x approaches -1 from the left, the limit, not the f of x, the limit is 0, because it's the height. We're talking about the height. The height of the graph of the function is 0. Here it is. So what is happening with this point? Nothing. That's actually f at -1. And nobody asks us about that. So completely ignore it. Limit has nothing to do with the value of the function at the point. Now, what is happening when x approaches -1 from the right? From the right, well, still 0. From the left and from the right, both limit met. Then the limit exists, and it is 0. And even though the function is discontinuous at this point, it actually has a hole, and it's called a removable discontinuity because we can remove it or fix it. Still, the limit exists because limit is something about approaching things, not about actually being at that point -1. But at least from the left and from the right, the function approaches this height like this. What is happening at 1? When x approaches 1 from the right, that's like this, from the right, f of x approaches height. What is this height? -1. -1. From the, that's from the left. I'm talking about this one, from the right. From the right, it is -1. Over here, -1. So this ends, the second answer is -1. But from the left, this one, from the left, f of x actually approaches deeper or lower height. That's -2. Okay, -2. -1 did not equal to -2, so we're gonna call it does not exist. And this is a jump discontinuity. That's not removable discontinuity. That's just a jump. That's it. That's how you do it from the graph, pretty fast. Just make sure you don't mess up with what we are asking about here. We're checking the height of the function as x approaches some kind of point. The height of the function as x approaches some kind of input. Well, hopefully this video was helpful, and now you're very confident with these topics and can do it by yourself. See you next time.